All right, it is 10, so let's get started for today. Um, Hopefully you've read my announcement by now, so you kind of know what's going on for the rest of the semester. Um, but let me just hit the big points here. Um, like I said on Wednesday, we have a few more questions to do for Lewis structures. And we're not going to do all of these in class. I just want to show you how to deal with double bonds and triple bonds and ions. And then we're going to move into the lecture that I have prepared for today. And for the lecture I have prepared for today, we're not going to get through all of it. That's okay. Wherever we end today, and I have a pretty good idea where I want that to be, that's going to be it for like test 4. So I'll make like a big note of that when we get there. And then anything else we have to cover for that PowerPoint, that will be covered next week, Friday, where that new information will show up on the final exam. And so tests next week, Wednesday, final exam, like I said, you have either May 6th or May 7th to take it. It'll be open for 48 hours. So whenever it's best for you, you can take it. It is cumulative. So it is going to cover everything that we've talked about. And there is one more portion, the take home portion of the exam, some questions. And for this, I believe I said that is due at midnight on May 10th. So if you are studying for the final exam or your final exams and you don't have time to work in the take home, that's okay. You have until May 10th. But do not wait till the last, do not wait till like 11 p.m. on May 10th. It might take you a couple hours to do. That's why I'm giving you a few more extra days. All right, so I think that's the big points. So what I want to do now, if there's no questions about that stuff, and there is, feel free to put those in or email me whenever. What I want to do is I want to go over A, B, and probably let's do A, B, and G, I guess, on Lewis structures, just so I can show you like some of the more complex ones. Then we're going to move on to Friday's lecture. So as a review, how to write Lewis structures is the first thing you want to do for a Lewis structure is write out the skeleton. So normally when you have carbon and hydrogen compounds, hydrogens are always at the termini. And for this, you'll have one hydrogen to each carbon. Now, the next thing you do is write out the number of valence electrons for each element. So hydrogen has 1. And carbon has 4. And remember, the name of the game here is that hydrogen needs 2 total electrons, carbon needs 8. So for the hydrogens, that's easy enough. We make a covalent bond between each carbon and hydrogen. So now each hydrogen has 2 electrons. Those are good. Carbon has 1, 2, 3, 4, 5. And this other carbon will have 5 too. However, they need to get to 8. And so the only way to increase the electron count when you have nonmetals is covalent bonds. So I make a covalent bond here. Now they go up to 6. However, we're not at 8 yet. So what we need to do is start making more bonds. So I make a bond here. That's 7. And I make another bond here. That's 8. Remember, every time you make a bond, you get to add 1 electron. So C2H2 would actually look something like this. It would form a triple bond because I need those sharing of those electrons to get carbon to get into 8. So just be aware when you're doing Lewis structures, if you come to the situation of, oh, I made a single bond, but my element doesn't have 8, and I need to keep making bonds, you are free to make double and triple bonds as you like, except the hydrogen, right? Hydrogen can only ever have one bond. Hydrogen is special. Why not add more H? Because you're not allowed to, right? The formula is C2H2. You only get 2 hydrogen to begin with. It's not like, so I think what you're thinking of is this problem. Where is it? Oh, it must have been on Monday, where we were like saying, what is the formula between nitrogen and sulfur? That's different than this type of problem. Here, I'm giving you the formula and saying, what's the structure? On that question, I was just saying, here's 2 atoms. What will be the formula? And for that, you use the structure. So just be aware of what the question is asking. So that's A. Now let's look at B. And B is the first time we have a negative charge. So with charges, if you have a negative charge, you gain an electron. And you gain the number of electrons based on what the size of the charge is. So if it's a -1 charge, you get 1 electron. If it's a -2 charge, you get 2 electrons. Same thing with positive charges. If you are a positive charge, you lose 1 electron. If you're a +2, you lose 2 electrons from your total amount of valence electrons. So let's see what that actually means for OH minus, right? So OH, oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6. Hydrogen has 1. And because we are a negative charge, we get a bonus electron to play with, right? So rules of the game, hydrogen needs to get 2. Everything else generally wants to get to 8. So I make a bond. Now hydrogen's at 2. Oxygen is at 1, 2, 3, 4, 5, 6, 7. And if this was a neutral compound, that would be bad because oxygen would stay at 7. However, since it's -1, we get to place this electron anywhere we want. So I can just take this and give it to oxygen, no problem. Now oxygen has 8. So the Lewis structure for OH minus looks like that. So that's how you handle Lewis structures with negative charges. So questions about that idea? Right, so the last one, G. The reason why I want to point out G is because this is one of these questions, one of these structures that, you know, when you're new at doing this, it's really hard to place everything. So here's a question. In the Lewis structure, why don't we have to put a negative sign by the H to show that that's the formula? So I guess it would be, I think you are actually correct where you would want to do something like that to show it's negatively charged. I just kind of forgot it. But yes, you're correct. You would want to show the charge in the Lewis structure to make it more correct than what I did. Yeah, so the brackets, I believe, is generally what you do. So the question is just make sure to put it in brackets. Generally, for Lewis structures, for whatever reason. I actually don't know why they do this, but they use brackets for charges when you're doing a Lewis structure. Maybe it's so people don't confuse it with a covalent bond. I don't know, but yeah, it's in brackets. All right, so for G, and this is something, if you learn more chemistry and take more chemistry classes, this is something that you just kind of learn naturally by looking at structures. But when chemists write structures, they are generally trying to tell you the best that they can what order the atoms are in. So here we have H3COCH3. So what I mean by that is that they are kind of, this formula is telling you the order of the atoms. And that's kind of a fast way to start to understand how these molecules look, because it should go, 3 hydrogens at the termini, then carbon, oxygen, carbon in a row. Now I assign my valence electrons to everything. Oxygen has 6. Hydrogen has 1. Carbon has 4. Then I start making bonds. So carbon to hydrogen, it's always 1 bond. Carbon to hydrogen, it's always 1 bond. So each hydrogen is taken care of. Carbon can make a bond here. Carbon can make a bond here. Everything now has 8 electrons. And so this molecule would look like that. So that is just another thing I wanted to point out. A lot of times when formulas are written out, they are telling you the order of atoms. And so for C, D, E, and F, I will put the answers up today for those, but I do want you to just, take 20 minutes, try to figure those out. If you can do C, D, E, and F, there's really no question I can ask you on the test for the final that you're not prepared for. So that's a good way to test yourself. So before we move on from this question, are there any questions whatsoever about Lewis structures? All right, let me switch PowerPoints here. It's the 23rd. And we're actually going to continue our discussion on Lewis structures and talk about the idea of resonant structures. And what a resonant structure is that it's a molecule that has 2 different Lewis structures, right? So in every example we've done up to this point, we've only done it where the molecules I've given you, there's only one possible Lewis structure to make out of that. But a lot of molecules, you can make more than one resonance structure, and theoretically they would each be possible. So different Lewis structures of the same molecule are called resonant structures. And the molecule in reality is like a combination of these resonance structures. So for example, for ozone over here, O3, there's 2 different Lewis structures you can have. You can have a double bond between these 2 oxygens, or you can have a double bond between these 2 oxygens. And in reality, you don't switch between the 2. The molecule isn't in one of these, but rather it's a combination. These dashed lines, you'll often see these for resonant structures. what these dashed lines mean are partial. Like this is partially a double bond. This is partially a double bond. And that's kind of a really deep concept to think about. What does it mean to be partial when it comes to a bond? So I guess the simplest way I can explain it is like it looks like a double bond, it behaves like a double bond, but it's doesn't have like the same strength of a double bond almost. Yeah, it's a really difficult concept, but just know it's like it's partially there. It's almost a double bond. It behaves like a double bond, but almost not. That's why your book has this image where they're trying to show that. It's almost like if we show molecules as dogs, let's say that your dog has two resonance structures between this dog and this dog. Well, your dog doesn't flip between the two states. Like you don't look at him 1 minute and he looks like that, and then you turn around and the next minute he looks like that. It's a combination of the mother and father, right? That makes a hybrid. So he's almost that type of dog. He's almost that type of dog, just a mixture of the two. Same thing going on with molecules. And there's a way to determine which resonance structure is actually better. And that's an idea called formal charge. Just note that formal charge is a concept made up by chemists. It doesn't exist in nature, in that it's not real, but it's bookkeeping that chemists can do to decide, okay, because the formal charge is this molecule is going to be more likely. So let's take a look at what formal charge here is. And formal charge is a score that you assign to each atom in a molecule. So here on this table, we have a chart. So let's look at structure A. The way we decide formal charge is first, let's look at hydrogen. You write down how many valence electrons comes with hydrogen. And hydrogen, as we have learned so far, when we write the Lewis structure, this looks like that. So it has 1 valence electrons. Then in the structure, you subtract the number of valence electrons from the number of non-bonding electrons. And non-bonding electrons are those dots we have left over that aren't in a bond. So hydrogen doesn't have any non-bonding electrons, so it's -0. Then this thing's really confusing, I think, -1/2, 2. So I think the easier way to do this is you do minus the number of bonds you have. So this would just be a -1 because hydrogen has 1 bond. So the total formal charge is 1 minus 0 minus 1 is 0. So hydrogen in this molecule has a formal charge of 0. Carbon starts with 4 valence electrons. So 4. In the final structure, there are no lone pairs, so -0. Then it has 4 bonds, so -4. Nitrogen, has 5 valence electrons. We have 2 left over, so 5 minus 2 for the non-bonding. And then we have 3 bonds. -3 is 0. So that's one structure we could do. Another structure of the same molecule is in B here. And if you look at that formal charge, I'm not going to go through the whole thing again, but you can see in A, we had all zeros. In B, we have a +1 and a -1. So generally, to decide which structure is better, you want all your formal charges to try and be 0 if you can. If you can't, you want your negative numbers on your most electronegative. Neg numbers on most electronegative. I'm not really understanding to see how many non-bonding electrons there are. So in the resonance structure, if we look at carbon, you can see there's 2 dots by carbon. That's 2 non-bonding electrons. Right? For H2O, if I was, whoops, let me do that better. H2O, the Lewis structure of H2O is like that. Oxygen has 4 non-bonding electrons. It's just those dots. Each dot is 1 electron, so that's 1, 2, 3, 4. Hydrogen doesn't have any because it has no electrons floating around it. That makes sense? Yeah, it's what electrons you have on the atom. Right? So for in structure B, carbon has 2 electrons not in a bond. Those are non-bonding electrons. So that's -2 because you have 2 of those. That's all it is. Yep. So you just look. So yeah, generally the better structure has more zeros. And if you do have a charge, you want the minus charge on the most electronegative atom. That's how we can tell which structure is better. So let's do this. And I'm going to do A to try and look at resonance structures and assign formal charges. So A is CO3 2-. So carbon is usually always a center atom. We have 3 oxygens, and I'm going to put them in a triangle. So helpful tip, usually when you have multiple atoms of the same type, they aren't interacting with each other. They are usually interacting with something else. So that's how I know the oxygens aren't going to be related. Okay, so there's my base structure. And then for the -2 charge, I get to play with 2 more electrons than I normally would. So if we look at the number of electrons, 6, 6, 6, 4. Remember, the goal is to get to 8. So I make 1 bond here, 7, then 5. Make 1 bond here. That would go to 6, 7. 1 bond here, 7, 7. All right, so I'm at 777. Carbon has 1 more electron. So let's just make it here. To make that another bond, that carbon goes to 8. This oxygen goes to 8. Now I just have to balance these 2 oxygens. Well, luckily I have 2 electrons left over. So I can put 1 there. And I can put 1 here. When I place those electrons, each goes up to 8. And so if I was to rewrite this, my first resonance structure looks like this. And that has this -2. That's one structure. This actually has a total of 3 structures. So this is one structure. Or what if I made the double bond to this oxygen? Or what if I made the double bond to this oxygen? Each one of those is valid. So each one of these is a resonance structure. So I have 3 resonance structures that I can make out of CO3 2-. Now the question is one resonance structure better than another? To do that, I need to do formal charges. So I'm going to number these as oxygen number 1, oxygen number 2, oxygen number 3. And it's always going to be that order, 1, 2, 3. 1, 2, 3. So for my most left molecule, let's look at the formal charges. Carbon, oxygen 1, oxygen 2, oxygen 3. I'm going to make a little table. So the first thing we do is valence electrons. How many valence electrons did each molecule come with? Carbon came with 4. Each oxygen comes with 6. So that's my first row. And I subtract that from number of non-bonding electrons. I'm going to write NBE. That just means non-bonding electrons. So in our first structure, carbon doesn't have any non-bonding electrons left over. There are no dots around carbon. So this is -0. Oxygen 1 has 1, 2, 3, 4, 5, 6. So -6. Oxygen 2 has 1, 2, 3, 4. So -4. Oxygen 3 has 1, 2, 3, 4, 5, 6. -6. And my next row is subtracting the number of bonds. So carbon has 1, 2, 3, 4 bonds, so -4. Oxygen 1 has 1 bond, so -1. Oxygen 2 has 1, 2 bonds, so -2. Oxygen 3 has 1 bond, -1. After that, you add up all the scores. So carbon 4 minus 0 minus 4 is 0. That was a bad 0, but that's supposed to be 0, not like 9. Let me redo that. 0. Oxygen 1 is 6 minus 1, which is a score of -1. Oxygen 2 is 6 minus 4 minus 2, which is 0. Oxygen 3 is 6 minus 1, which is -1. So some things to note about this. The total formal charge is equal to -2 here. Your formal charge must equal the charge of the molecule. It has to. If it doesn't, you did something wrong. So our formal charge is -2. The charge on the atom is -2. So we're good there. That's fine. You notice we have 2 negatives. However, they are on oxygen. Oxygen is more electronegative than carbon, so that's okay. If in this structure we had a negative charge on carbon instead of oxygen, that would be bad because it needs to be on the most electronegative atom. So that's good. So this is a complete assessment or formal charges to our first structure. We could do the same thing for the second structure and the third structure, but we would get the same numbers just on different oxygens, right? In the third structure, or in this structure, the formal charge of oxygen 1 would be 0. Oxygen 2 would be -1. Oxygen 3 would be -1. In this structure, it would be -1, 0, because it's the same exact math, just different oxygens are being bound to. Since we have 3 structures with the same formal charge, there's like no difference. All 3 of these structures are valid resonance structures, and they all have equal probability. So it's going to be the actual molecule is going to be that hybrid we talked about on the previous slide with the dogs, where we would have those dashed double bond lines. So writing out the chart helped us verify we have oxygen with a -2 charge, and you said that's called the formal charge. So we don't have oxygen with a -2 charge. We have a molecule with a -2 charge, which we saw on the formal charges. The formal charge are these numbers I'm underlining right now, where it's valence electrons minus non-binding electrons minus the number of bonds. That's the formal charge. And what a formal charge does is if we have multiple resonance structures, they help us decide which resonance structure is better. If the formal charges of all the different resonance structures are basically the same, which is what's happening here. By basically the same, I mean the only difference is which carbon has a resonance score, a formal charge of 0, and which one has a -1. The only thing that changes between those 3 structures is moving around that 0. So there's no difference. What that tells us is that these 3 structures are equally good because we cannot distinguish them based on formal charge. And so CO3 2- is a hybrid structure, which has these partial double bonds. That's why I drew those dots. That is, in a nutshell, what is going on here. So what I would like you to do now is for B, I want you to try and write out the different resonance structures there are and try and determine the formal charge on each atom using our CO3 2- as your template for how to move forward. So I'm going to give you a couple minutes to do that. If you get stuck, have questions, please let me know. Otherwise, let's try it out. All right, so hopefully you had some time to try that out. At least get somewhere on that. I'm going to clear all this away and do NO2 minus then. So first things first, let's draw our skeleton structure. As for CO3, when you have multiple, especially oxygens, they're not going to be bonded to each other most of the time. Some molecules are, but nothing in Gen Chem 1 that I would ever throw at you would have that. So we're always going to assume multiple oxygens will be bonding to our center atom here. Right. Now the number of valence electrons. Nitrogen has 5. Oxygen has 6. And then it is -1 here. So that is the number of valence electrons we have. Now let's try and make everything have 8. Make a bond here, make a bond here. Our score would be at 7. 1, 2, 3, 4, 5, 6, 7 for nitrogen, and 7 here. So I can make one more bond because nitrogen has 1 unpaired electron. So 8. 8. Have this one left over. I can go here. So one resonance structure would look like this. And the other one would just have, and so -1. The other one would just have the double bond. That's a weird arrow, but it would just have the double bond over here. So let's do our formal charges now. So it is the number of valence electrons that we had. So O and O. So oxygen comes with 6, nitrogen comes with 5, oxygen comes with 6. And let's do it for this molecule at the same time. Why not? So that was a bad line. Erase that. So, and we are separating our molecules here. So this also has 6, 5, 6. Right. So that's valence electrons minus number of non-bonding electrons. So the number of dots surrounding our molecule. So this has 1, 2, 3, 4, 5, 6. So -6, 1, 2, -2, 1, 2, 3, 4, -4. This molecule has 4, then 2, then 1, 2, 3, 4, 5, 6. Take that minus number of bonds. So -1 for 1 bond, -1, 2, 3 for 3 bonds, -2 for 2 bonds. Oxygen -2 for 2 bonds, 1, 2, 3 for 3 bonds, 1 for 1 bond. So we should make a chart for all possible resonance. Yeah, in general, you want to do that because I don't think we're actually going to have time for it. The next question, question 2, we might actually have time for it. We'll see. The question 2 is, which resonance structure is better? Because here, A, B, and C, all the resonance structures are the same, which we're going to see here in a second. That's not the point. That is not for question 2. So yeah, for every resonance structure, you generally want to do a chart when you're first starting out to see which one's better. If you decide to do chemistry for a couple of years, you start to build up that intuition where you can look at a molecule and know which one's better. But I'm guessing we're not there yet. So formal charge on this oxygen is -1. This nitrogen, 5 -2 -3 is 0. This oxygen, 6 -4 -2 is 0. So overall, the formal charge is -1, which is good because our charge is -1, so they have to match up. And we have a negative charge on an oxygen. That's good because oxygen is more electronegative than nitrogen, so the charge would have to be on oxygen. We do the same thing over here. 6 minus 4 minus 2 is 0. 5 minus 2 minus 3 is 0. 6 minus 6 minus 1 is minus 1. So formal charge overall is minus 1, which is good. And it's on the oxygen, which is good. There's no difference between these two structures. It's either do you have a charge on this oxygen or this oxygen, which means they're both equally good, which means you will have a hybrid. All right. Now that you saw me do A and you had a little chance to work with B, is there any questions about this idea of formal charges or resonant structures? How would I write out the hybrid for B? Basically what you do is if you have a double bond flipping, you just put those dots there and saying this has a partial double bond, this has a partial double bond. So for any case where you have that double bond going, and those of you who plan on taking organic, you will see this concept a lot, but that's what you do. And if you are planning on taking organic, burn this concept into your mind right now. Remind yourself to look back at it. There's a lot of resonance structures in organic chemistry. All right, so for C, I'm going to leave C as one of those like you can do for more practice. I do want to just get on the question 2, and that will be the last thing that we do. And it's what happens if you do this exercise and you have resonance structures with different formal charges. So in the last question, our resonance structures were like more or less always the same, and that the only difference was which like oxygen has a negative charge. But you can make resonance structures where you do have some differences in formal charges. So in general, the rule of thumb is the fewer formal charges, the better. And what I mean by that is the more zeros, the better. The more atoms you can have with a score of 0, the more correct your structure is going to be. And if they do have formal charges, you want them to be as small as possible. All right, big formal charges are bad. Small formal charges are good. And like I was saying, if you have a negative formal charge, it has to be on your most electronegative atom. Remember, we looked at the chart of electronegativity on the periodic table. Your most electronegative atoms are in the top right. Your least are on the bottom left, and that's the trend. So make sure the atoms in the top right have that negative formal charge. And so the exercise here is I give you 2 structures, A and B. They're separate questions. And I want you to decide, using formal charges, which structure is written out the best. So in the time remaining here, let me just go through A. So the first thing we want to do, I'm going to name this, it doesn't matter, the hydrogens are the same. So what I'm going to do for A, right? So we have structure 1 and structure 2. Structure 1 and structure 2. We basically have 3 atoms: hydrogen, carbon, sulfur. The reason why I'm not listing the hydrogen separately, which you can do, is they're the same. There's no difference. And then number 2 has hydrogen, carbon, sulfur. So Number of valence electrons. Hydrogen has 1. Carbon has 4. Sulfur has 6. How I'm figuring this out so fast is hydrogen always has 1. Carbon always has 4. Sulfur, I had to think about there for a half a second. Sulfur is right below oxygen on the periodic table. So anything in that column always has 6. So 1, 4, 6. Again, if you're confused about how to get these numbers, just write out the electron configuration, right? Carbon is helium 2s2, 2p2, right? That's how we're getting valence electrons, just in case you forgot that. So that's the number of valence electrons. I'm going to subtract that from the non-bonding electrons. So in molecule 1, hydrogen doesn't have any, carbon doesn't have any, sulfur has 1, 2, 3, 4. So minus 4. Here on number 2, hydrogen doesn't have any, carbon has 1, 2, 3, 4. So minus 4. Sulfur doesn't have any. Oh, I'm running out of space, so it's going to be under here. So non-bonding electrons, that looks like a W, but that's an N, minus number of bonds. Hydrogen has 1 bond, so minus 1. In structure number 1, carbon has 1, 2, 3, 4, 4 bonds. Sulfur has 1, 2, minus 2. In structure number 2, hydrogen has 1 bond, minus 1. Carbon has 1, 2, minus 2. Sulfur has 1, 2, 3, 4, minus 4. Now let's add up formal charge. So hydrogen is 1, 0, minus 1, which is 0. Carbon 4, 0, minus 4, 0. Sulfur 6, minus 4, minus 2, 0. All zeros. That's what we want to see generally. Number 2, 1, 0, minus 1, 0. 4 minus 4 minus 2 is minus 2. 6, 0 minus 4 is plus 2. All right. So now we have 2 resonance structures that have different sets of formal charges. And to pick the best one, like I said, you generally want zeros. The more zeros, the better. So structure 1 is better because the formal charge on every atom there is 0. And for 2, it's not. So that is how we can start to decide, if we have like big structural differences. So like here we have a carbon in the center versus a sulfur in the center. If we want to decide which one is more accurate, we would do formal charges. So this molecule would actually exist as structure 1 and not as structure 2. So that is the practical uses for formal charge there. So any questions about that? All right, so we are out of time here. So we're gonna say this last slide for test 4. On Monday, you just have a little bit more to go. So yeah, anything else we cover on Monday won't be on test 4, but it will be fair game for the final. So yeah, let me know if you have any questions about studying moving forward. But yeah, I have nothing else for you. So I hope you all have a good weekend. Questions that always are welcome. If you want to have some tutoring sessions or even group tutoring sessions, just let me know. We can set up something on Zoom. That's no problem. Otherwise, hope you learned something today. Hope you enjoyed your time here somewhat. And I will hopefully see you all on Monday. Oh, my face is really down there. Okay. Take care, everybody.